Sharks represent an amazing group of cartilaginous fish whose evolutionary history spans over 400 million years. These ancient creatures outlived the dinosaurs and several mass extinctions, retaining unique structural features: a streamlined, torpedo-shaped body, a powerful heterocercal tail, and multiple rows of constantly replacing teeth. Their skeleton, composed of cartilage, contains no bone tissue, making these creatures perfectly adapted to life in the aquatic realm. The modern world of sharks is astounding in its diversity. Over 500 species are known, ranging from the dwarf lantern shark, measuring just 17 centimeters long, to the colossal whale shark, reaching up to 20 meters in length. These fish have colonized all latitudes of the world ocean, from tropical lagoons to Arctic waters, from surface layers to depths exceeding 2,000 meters. Interestingly, some species, like the bull shark, are capable of migrating from saltwater into freshwater rivers and lakes. Although most sharks are active predators, their diets are extremely varied. 3 filter-feeding species stand apart: the whale shark, the basking shark, and the megamouth shark. These marine giants feed on plankton, filtering thousands of cubic meters of water through a specialized apparatus. This evolutionary path demonstrates the remarkable plasticity of the group, which has managed to occupy completely different ecological niches, from benthic hunters to pelagic wanderers of the open ocean. The shark's skeleton represents a unique evolutionary adaptation. It completely lacks bone tissue and consists of cartilage. Recent research has shown that this is not a primitive trait, but rather the result of a secondary loss of bone during evolution. Anatomically, the skeleton includes several specialized sections: an axial skeleton with amphicoelous vertebrae, a cartilaginous skull with a rostrum, and girdles for paired and unpaired fins. The axial skeleton is formed by the vertebral column, where the notochord passes through all the vertebrae. The shark's skull is a monolithic cartilaginous structure with orbits on the sides and a brain case between them. The rostrum, the anterior projection of the skull, provides support for the snout and sensory organs. A structural peculiarity is the absence of a direct connection between the pectoral fin girdle and the axial skeleton. The fins attach to a cartilaginous arch embedded within the musculature. The structure of the fins reflects sexual dimorphism. In males, the basal element of the pelvic fins is modified into pterygopodia, a copulatory organ. The unpaired fins, dorsal, anal, and caudal, are supported by radials and elastotrichia. The heterocercal tail, where the vertebral column extends into the upper lobe, ensures efficient forward movement. This cartilaginous construction combines strength with flexibility, making the shark an excellent swimmer. The placoid scales of sharks are an evolutionary masterpiece, the most ancient type of fish scale, performing multiple functions. Each scale is a rhombic plate with a sharp spine, identical in structure to a tooth. These dermal denticles consist of dentin reinforced with a mineral apatite and covered with vitrodentin, an analog of enamel. Thanks to this composition, the scales form an extremely strong yet flexible protective layer, resembling chainmail, which safeguards the shark from both large predators and parasites. The hydrodynamic perfection of shark skin is the result of the unique structure of its scales. The textured ridges on the dermal denticles create microscopic vortices that reduce turbulence and water resistance. This enables phenomenal speed. The mako shark, capable of bristling its scales, can reach 80 kilometers per hour. An additional benefit is silent movement. Unlike bony fish, sharks do not generate acoustic waves while swimming, remaining invisible to their prey until the very last moment. The muscular system of sharks demonstrates unique specialization, reflecting their predatory lifestyle. It is divided into 3 functional groups: cardiac muscles, ensuring the continuous work of the heart; visceral musculature, controlling the internal organs; and somatic musculature, responsible for body movement. It is the somatic musculature that is of particular interest. It is organized into segments, myomeres, separated by connective tissue septa, creating an efficient system for undulatory movement. A key feature is the division of somatic musculature into 2 fiber types. Red muscles operate aerobically, providing endurance swimming. White muscles, responsible for sudden bursts and high-speed attacks. Evolutionary adaptation has resulted in a relative autonomy of the muscular system. The muscles retain the ability to contract even when the connection to the CNS is disrupted. However, this specialization also has metabolic limitations. Sharks cannot control the contraction intensity of white muscle fibers, leading to rapid lactic acid buildup. These metabolic limitations pose a serious threat to shark survival. Research has shown that a lactate concentration of just 10 to 15 millimoles per liter can already be fatal for many species. Highly active species like the mako shark are especially vulnerable. A lactate concentration of 30 millimoles per liter leads to irreversible lactic acidosis. This data explains the high mortality rate of sharks after catch-and-release fishing and underscores the fragility of their metabolic system, which is perfectly adapted for short, intense bursts, but not for prolonged stress. The dental system of sharks represents a unique evolutionary mechanism where teeth, which are modified placoid scales, are arranged in multiple rows and are constantly replaced in a conveyor belt-like fashion. This feature ensures predators maintain a consistently sharp dental apparatus throughout their lives. Tooth shape directly reflects the dietary specialization of the species. Bottom-dwelling sharks that feed on crustaceans have developed flat, crushing teeth with a ridged surface. Active predators like sand tiger sharks have long, sharp teeth for impaling prey. Tiger sharks possess wide, serrated blades for slicing large prey, and plankton-feeding giants have small teeth up to 5 millimeters, serving more of a retaining function. The caudal fin, tail, of sharks demonstrates no less impressive adaptation. Its heterocircle structure, with an enlarged upper lobe, provides efficient forward thrust. However, in high-speed species like the mako shark and the great white shark, evolution has shaped an almost symmetrical tail close to homocircle, enabling them to reach speeds of up to 50 kilometers per hour. In slower species, the upper lobe is significantly dominant, generating downward thrust and creating lift to compensate for the lack of a swim bladder. Each tail's shape perfectly corresponds to the ecological niche of its owner, from maneuvering through reefs to pursuing prey in the open ocean. The respiratory system of sharks is a unique evolutionary mechanism refined over millions of years. Unlike bony fish, sharks possess 5 to 7 pairs of gill slits, which, like arch structures, are supported by cartilaginous septa. Each gill slit leads to a separate chamber housing respiratory folds that form the demi-branches, gill filaments. A key feature is the countercurrent exchange system. Blood in the capillaries flows in the opposite direction to the water current, allowing for the extraction of up to 80% of dissolved oxygen, nearly twice as efficient as in most bony fish. The breathing process resembles the action of bellows. During inhalation, the pharyngeal area expands and water rushes in through the mouth and the spiracle, a special opening behind the eyes, retained from ancient ancestors. During exhalation, the gill arches contract and valves open, expelling water. Interestingly, some bottom-dwelling species, like carpet sharks, can lie on the seabed for hours, pumping water through their spiracles, while pelagic species must constantly swim to ensure gill ventilation, ram ventilation. The cardiovascular system of sharks demonstrates an ancient yet effective design. The two-chambered heart, located near the head, pumps only venous blood through a single circulatory circuit. The blood contains a specific hemoglobin adapted to cold waters, but its concentration, 3.4 to 6.5%, is significantly lower than in bony fish. The oxygen-carrying capacity of the blood does not exceed 8.7%, reflecting a lower metabolic rate. This is compensated for by a powerful muscular pump. During swimming, muscle contractions help push blood through the vessels, creating additional pressure. This feature explains why many sharks die if they stop moving. Their hearts simply cannot manage the blood supply for their large bodies without muscular assistance. The digestive system of sharks represents a unique evolutionary complex, perfectly adapted to a predatory lifestyle. Their famous teeth, which are modified placoid scales, are arranged in multiple rows on mobile cartilaginous jaws, forming an ideal cutting tool. After capturing prey, food passes through the pharynx into a U-shaped stomach, where it begins to be processed by gastric juice of incredible acidity. The concentration of hydrochloric acid reaches 3%, allowing it to dissolve even bones and shells. A distinctive feature of shark anatomy is the spiral valve in the large intestine, an ancient evolutionary mechanism that increases the absorptive surface area of the intestine without increasing its length. The rectal gland serves a dual function. It regulates salt balance and, during the breeding season, secretes a fragrant substance that acts as a pheromone. But the true wonder of nature is the giant liver of sharks, reaching up to 30% of their body mass and consisting of 70% fat reserves. This organ serves both as an energy depot and a natural float, compensating for the lack of a swim bladder. Unique digestive adaptations allow sharks to demonstrate remarkable metabolic efficiency. The enzyme collagenase ensures the rapid breakdown of the prey's connective tissues, and their ability to endure prolonged fasting reflects their energy-saving strategy. For instance, a 3-meter-long sand tiger shark manages with just 80 to 90 kilograms of fish per year, and a great white shark can go without food for up to 1.5 months. Completing this perfect system is the mechanism of stomach aversion. Sharks have learned to safely evert their stomachs through their mouths for cleaning, without damaging it with their sharp teeth, demonstrating astonishing control over their own anatomy. The reproductive system of sharks demonstrates remarkable evolutionary adaptations that ensure offspring survival in the harsh ocean environment. Unlike most bony fish, which practice external fertilization, sharks possess a sophisticated system of internal fertilization. Males use pterygopodia, modified pelvic fins, to introduce sperm into the female's cloaca. This mechanism guarantees successful fertilization even in the open ocean. Nature has developed 3 unique reproductive strategies for sharks. Oviparous species, comprising about 30% of all sharks, lay eggs in sturdy, horn-like capsules, often with tendrils for attachment to seaweed. These mermaids' purses protect the embryo from predators and provide it with nutrients. Ovoviviparous species retain the eggs within the uterus, where the pups hatch and are born fully formed. The most advanced strategy is viviparity, where a placental connection forms, allowing the embryo to receive nourishment directly from the mother's bloodstream. Embryonic development in sharks is astounding in its diversity. In sand tiger sharks, intrauterine cannibalism occurs. Embryos with developed teeth consume their siblings, and only the strongest individuals are born. Porbeagle sharks practice oophagy, feeding on unfertilized eggs. Gestation periods vary from a few months to a record 2 years in the spiny dogfish. Parthenogenesis, accidental virgin birth, observed in captive individuals where a female produces offspring without a male, is of particular interest. These reproductive strategies ensure high offspring survival rates for sharks. Newborn pups are born as fully formed predators, up to 1.5 meters long in some species, capable of hunting independently immediately after birth. This qualitative approach to reproduction compensates for low fecundity compared to bony fish and explains how these ancient predators have maintained their dominant position in marine ecosystems for millions of years. The established image of the shark as a solitary creature has proven to be a serious oversimplification. Many species exhibit surprisingly complex social behavior. In the Gulf of California, aggregations of hundreds of scalloped hammerhead sharks regularly form, and the migratory routes of some species are more complex than those of migratory birds. Hierarchical relationships even manifest between different species. For instance, oceanic white-tip sharks dominate silky sharks of the same size during food distribution. Sharks have developed a sophisticated communication system. When threatened, they use special threat displays. They increase the amplitude of their swimming movements, with the intensity of these signals corresponding to the level of danger. Research from 2023 confirmed that the brain-to-body mass ratio in many sharks is comparable to that of birds and mammals, explaining their capacity for problem-solving and social interaction. A striking example is a documented case in South Africa where 7 great white sharks coordinated their actions to jointly pull a whale carcass off a sandbank. The ability to rest varies among shark species. Many benthic species can lie on the seabed, pumping water through their spiracles, while their eyes remain open. Spiny dogfish exhibit a remarkable adaptation. They can sleep while swimming, as movement is controlled primarily by the spinal cord. It is hypothesized that some species, similar to dolphins, might rest different brain hemispheres alternately. The cruising speed of most sharks is around 8 kilometers per hour, but they are capable of impressive bursts of speed during an attack. The short-fin mako shark, thanks to its regional endothermy, mesothermy, can reach speeds exceeding 50 kilometers per hour. Their play behavior is no less fascinating. Instances have been observed where porbeagle sharks played with seaweed, indicating advanced cognitive activity and curiosity that goes beyond basic instincts. These observations fundamentally change our understanding of sharks as primitive creatures, revealing a complex world of social interactions and cognitive abilities. The image of the killer shark, created by popular culture, has little to do with reality. The probability of being a victim of a shark attack is 1 in 11.5 million, and the chance of dying from such an attack is only 1 in 264 million. For comparison, in the United States, over 3,300 people drown annually, while fatal shark attacks number in the single digits. Even bees and lightning pose a significantly greater threat to humans than these marine predators. Of the more than 500 shark species known to science, only 4 pose a significant danger: the great white, tiger, bull, and oceanic white-tip sharks. They are responsible for the majority of recorded fatal attacks. Another dozen or so species can show aggression, but their attacks rarely result in death and usually occur due to human provocation or mistaken identity. A shark's behavior before an attack typically follows a certain pattern. First, the predator studies the object, swimming around, and assessing the potential prey. This may be followed by tactile contact, the shark gently mouthing the object. The final attack occurs suddenly and unexpectedly. It's important to understand that most attacks are acts of curiosity, not targeted hunting of humans. While absolute protection doesn't exist, certain measures can reduce the risk. Avoid swimming at dusk and dawn when sharks are most active. Don't enter the water in areas with seal or sea lion colonies, the natural prey of sharks. It's also better to avoid swimming in murky water with poor visibility and to refrain from wearing bright jewelry that might attract the predator's attention. So, what have we learned? A shark is not just a mindless killing machine, as it's often portrayed in Hollywood blockbusters. It is the pinnacle of evolution, a perfect predator honed by millions of years of natural selection. They are living symbols of power, grace, and incredible adaptability. From the whale shark peacefully filtering plankton to the great white reigning at the top of the food chain, each plays a vital role in the health of the ocean. Our fears of them pale in comparison to the real threat we pose to them. Overfishing, water pollution, and climate change. These are the true enemies of these amazing creatures. So let's replace fear with respect and myths with knowledge. Because by protecting sharks, we protect the entire world ocean. And ultimately ourselves. Thank you for joining us on this dive into the amazing world of the ocean's rulers. If you liked the video, don't forget to subscribe, like, and comment. This will greatly help the channel and help more people see this video.